Good afternoon, everybody. We are ready to start. So first of all, welcome. It's well, nice surprise to see many people and a lot of new faces where they did not meet yet. So thank very much for attending. My name is Francesco Pizzocolo. I'm the project manager of the HEAT-INSYDE project, and I'll be the moderator today. So just very quickly through our program. So we are going to start with introduction about what is the project is about, and it's going to be given by Olaf Adan. Olaf is the project coordinator of HEAT-INSYDE. So as you see, he's working for TNO as a principal scientist professor at the TUI, and then recently found together with Pim Donkers Cellcius, that is the company that is moving to a commercialization the heat battery. Then the second presenter, we are going to actually go a bit into the technology, and the two presenters are Professor Henk Huinink, that is our material expert, professor here at the TUI, and already leader in several EU projects on the topic. And the second presenter is Pim Donkers, as mentioned, is one of the founders of Cellcius, and is going to drive you a bit into the hardware part of the battery. Next presentation will be given by Bart Erich, that is about how the heat battery is going to be integrated in the future energy system. Bart is a senior scientist at TNO and also lecturer at TUI, and recently also starting a company called Calosol, that is going to explain a bit more later about it. Then, well, as every big project, we need to have an external advisory board. So it's basically a group of experts that need to check that what we do still makes sense, and not that we do it only because we love to do it. And two of these people are here talking to this audience today. One is Marc Linder, that is going to talk about how the also other technology for heat storage for balancing energy surplus and demand. So Marc is a group leader at DLR, that is the German Aerospace Institute, and is a group leader in the thermochemical system. He has plenty of publication and patent on the topic, so he's a real expert and was really one of the guidance for us during the project. And the last presenter is going to say something about the point of view of the policy and the regulator. So I'm going to talk about how heat storage in the current political environment. And the talk is going to be given by Nic Castellucci, that is leading battery storage project development at TMEIC Europe, and is working on energy storage topic for more than 10 years. But this is already enough for me. I almost forgot one of the most important things of the afternoon, in which we are actually going to see the smart heat shed, so where the heat battery is installed. So after the panel discussion, we will have to work together, because unfortunately the heat shed is on literally to the other side of the TUI campus, but we can go there together. And well, it's enough for me. So welcome everybody again, and I'd like to give the word to our first presenter, that is Olaf Adan.
Right, okay. So it's my real pleasure to give you a very brief introduction into the project HEAT-INSYDE. As Francesco said, I'm the coordinator, and it's really a privilege to do that job, leading such a great team and a great project. So HEAT-INSYDE is a European project. It's basically funded in the Horizon 2020 program. And HEAT-INSYDE is aiming to bring what we call an affordable, compact and sustainable heat battery solution closer to the residential market. And that statement basically underlines two things. First of all, we are working on a heat battery, which is basically a device that is storing energy and is delivering heat to the end user. Secondly, the focus of the project is really on the residential application, meaning that we are targeting a real implementation of the heat battery in a home. The project is bringing together 14 partners, so the slide is saying 30, but we are still growing, spread amongst 3 amongst 6 countries, European countries. We started already in 2019, and the project is running till March 2024. So in terms of duration, we are at 2/3 of the project, and we have a project budget which is sized close to 8 million euros. So, as I said, HEAT-INSYDE is a so-called innovation action, meaning that it's not only about technology, but it's about bridging the gap between technology and the market. So bringing technology into application. And in order to do so, HEAT-INSYDE is also having 3 what we call user-centric demonstrations where we validate the technology. 3 different demonstrations spread over Europe in 3 different climatic zones, being in the Netherlands, in France, and in Poland. And the first demonstration is really about to start now. So, who are we? I'm not going to introduce all the partners separately, but HEAT-INSYDE is mobilizing basically all the key players in the manufacturing chain as well as in the distribution chain. And if I'm talking about manufacturing, that's not only about, that's first of all about the material, but also about the hardware of the device, as well as about the implementation of the device in the energy system. And the consortium is supported by 3 technological players, TNO, Eindhoven University of Technology, and CEA from France. Well, basically, we didn't start from scratch. What you see on this slide is the 2019 7 kilowatt-hour demonstrator, which was a joint effort of both TNO and Eindhoven University of Technology, which basically proved that the concept worked. And this was really the first one about 3 years ago, and later on in this afternoon we will see where we are right now. This demonstrator was based on 2 main breakthroughs. First of all, if you would like to develop a rechargeable battery, you need a material that is also capable of being cyclic stable. You should be able to load and unload the material many times. That was the first breakthrough. And the second breakthrough is a system concept that is able to use the full potential of that material. And so we developed what we call a closed loop concept, which basically is a system with recirculating air at low pressure, and only containing 4 key components: a heat exchanger, of course, to add and to extract heat from your system, a ventilator to circulate the air, an evaporator condenser to add or extract water vapor from the system, and the most important part, that's the unit where the interaction between water vapor and salt is taking place, the reaction vessel. Basically a system that is using also mature technology. Now, if you talk about those components, 3 of the 4 are really mature components, thereby being cheap and also allowing us to make the steps towards the market very, very fast. Well, this first demonstrator also proved the unique selling points of the concept. Starting with the fact that this is a storage device which is really loss-free. So once the energy is stored, it remains there without any loss. Secondly, it's a very compact solution, meaning that if you talk about the energy density of the system, it's far more compact than water, which is the common way of storing heat in practice, and even more compact than the best lithium-ion battery that's on the market. Thirdly, it's affordable. And affordable, you can specify it in many ways, but it's far more cheaper than electric battery solutions. Far more cheaper. Fourth, it's sustainable. We are using material that is inherently safe. It's non-toxic, non-corrosive, non-flammable, and it's very easy to recycle. And apart from that, the eco footprint of the base material is excellent, and as well as the system has been designed for fully reuse. Fifth, it is a very versatile solution. So it is delivering heat. That's why we call it a heat battery, but it can be charged by either electricity or heat or both. And then there's one more thing, and that's the, let's say, the sixth unique selling point, and that's that cooling, the cooling option. We're talking about heat, but basically also cooling is becoming very important, that the cooling option is inherently included in the concept. So this is basically where we started from 3 years ago, and this afternoon we will just face where we are right now. So thank you very much.
Thank you very much, Olaf. I really hope that you all have a lot of questions, but I'm gonna ask you to hold them for the panel session after the coffee break. So for the next presentation, I'd like to ask to come on stage Henk, and together with Pim, we're going to go into detail into the technology.
Thank you. I'm going to say a bit more about the engine. And to start with this, I want to show you a large crystal. This is not what we use in the battery. And in the upper graph, you see a transparent one. And then if you would leave that on your desk on a dry day, I mentioned a dry day, you will see that it will become a bit whitish. And you can ask yourself, why is that the case? Now, if you zoom in on that, and that's how, as physicists, you look to this, you see atoms, you see molecules, you see water molecules. And that's basically it. So the transfer from transparent here to the whitish thing is because water gets out. Small notion. If you look to the amount of energy involved per water molecule, it seems to be small. But remember, there are a lot in there. How does it work? Then more practically. So you have salt, in this particular case we use potassium carbonate. You bring it in contact with water vapor, heat comes out because the water binds, let's say, to the vapor, and you can reverse that. And due to the fact that you can reverse that, that gives you an opportunity to store heat and also get it out again. Going a bit more on, let's say, what that could mean in terms of devices, and Pim is going to say a bit more about, I think, the device itself, but here you see the basic cycles. On the left, you see basically the discharge cycle. So you have the dry salt, there is no water absorbed in that, that's the green part. Then you see, in the left down corner, you see a point where, let's say, air is flowing up till a water vessel. There water evaporates. You bring that to the salt. The water becomes in contact with the salt, and then heat is delivered and then given away in the upper down left corner towards the heat exchange, and you extract it for use. And that's something you can, of course, reverse. So now zoom in to the right graph for you. Again, going down to the heat exchanger, you bring in heat. With that, you get warm air, you evaporate, now I'm going to, sorry, I'll make a mistake. You have warm air, you bring it down to the salt. There you drive out the water, and the water you condense basically in the condenser again. And this is basically the charging cycle, because you charge it by drying. A few words to make a bit understandable what it means in terms of technology development. And water goes into a salt, is built in there on a molecular scale. And that means, of course, bringing in space. You need space for the water molecule. Now, if you then start to think about developing materials, of course, it's not only about having a powder and being able to throw that in a device. And because if you bring in a powder, I can already assure you, that doesn't work. So you really have to manufacture dedicated particles. And there's a kind of optimization pyramid in that. You have different properties. Logical, technological properties, kinetics, there should be sufficient power output, so the material should respond fast. It should be stable, of course. but also it should be manufacturable. And there you see also a bit that sometimes these different, let's say, requirements are a bit contradictory with respect to the size of the particles. For speed, you want to have small particles, for power, and for manufacturing, you want to have big particles, easier to manufacture. Now, this is a bit the pyramid we have worked already for the last years. A bit of a glimpse, this is how the most recent version of the particle looks like. And you see a bit of key numbers with respect to the, let's say, the output characteristics in terms of energy density, in terms of power output, and in terms of also cost, estimated cost. And here I don't refer to the cost as how we made it, but based on predictions, for example, from partners colleagues who have experience with that, about what it could mean if you scale it up right now. With that, I want to hand over to Pim.
And around the material, we need a device. And a device we produce together with Bissol, with TBRM, CAA, and TNO. What you will see here on the picture is the graphical impression of the battery. And in the last 3 years, we made that into a real battery. Now, yeah, you still see a drawing. And here you see the blue part with all the TCM vessels. So there the active material is located in. And on the left side, you see the yellow bars, the yellow part, and that's with all the smart parts of the battery. Heat exchangers, ventilator, evaporator, condenser, that all is integrated in the left part. And these two have to interact on the right way with each other. Now, first of all, if you look at the KPIs of the device which we created, they were talking about capacity. And capacity is how much heat can you store in a battery with only one hydration-dehydration cycle. So it's not saying anything about how much heat you're getting out of the battery in total over a year or over 10 years. No, only once an hydration-dehydration cycle. And then we're talking about 200 megajoule. And what you see, you see here 10 boxes. And we can change, we can change the capacity quite easily. So we have 2 rows of 5 boxes, and we can enlarge that or make it smaller. So we have a modular system in a way of capacity. The other thing is charging power. We're charging here, we can do that with solar collectors, with PV, or with just grid electricity. So any energy which we can put in, and it ends up for our system in the power in the order of 500 to 4,000 watt. Discharging power is a little bit lower, meaning that we can discharge a battery between 500 and 2,000 watt. And that's important to know that at this moment we are foreseeing the battery not as a standalone version, but we're always having it in cooperation with a heat pump and a buffer vessel. And meaning that the high powers, which you need for taking a shower, will not come directly from the battery, but we are going to use that in combination with a short-term storage. And last but not least, what I said already, we are integrated in an entire system. Bart will explain more about that. But because of that, we are going to increase or decrease the electricity consumption of the entire house. But in this battery, of course, we also need some electricity. Not to charge it, but really to keep it running. You have ventilators in our system, which is bringing the airstream, the humid airstream, to the TCM. And to keep that in a decent level, we designed our battery in such a way that our electricity consumption is always less than 10% of the heat output. So talking in the terms of COP, we have a COP of 10 or higher. Now, how does a battery look like? So I showed you the picture, and you will see in a few hours how the battery really looks like. But this is how we build it up. So what you already see, it contains of small parts which you can build in on every house, on every location, as long as you have a floor space left in the order of 1 by 1 meter. But we can bring it in with small packages and we can build it up. Building up such a battery is in the order of 1 hour done. And then the 3 KPIs which I would like to show in more detail. One is the modular concept. what I already explained. We have a certain amount of boxes, 60 boxes in total in the first version, which we could build up. And now we have already a smaller one. So the modularity of the system is really high. Each box contains 25 kilograms of active material, and that also means that you can lift it by one person. Why do we have such a small box? It's because we would like to be able to charge and discharge a battery with small amounts of heat. If you have a large vessel, just one large vessel of 1 cubic meter, you have to heat up the entire vessel before you will be able to do the chemical charging of the battery. So heating it up, that's not an issue, but then you have only the heat capacity of the battery covered, but you would also cover the chemical reaction, so really removing the water from the salt. For that, using smaller boxes makes it easier to have a quick charging and discharging cycle. The other thing is our design. We changed our design in comparison with previous projects from a circular design to a rectangular design. And what you now see is, Olaf showed already the old version, a really large battery. In 2021 we had it was also a large battery, but it was already, the dimensions were already different. And we see in the component box and the battery next to each other, but they were not integrated. And now the 2022 version is a really integrated battery, active material, and component box. So that is the step which we made forward. And due to the design changes, and that's one, going from a circular one to a rectangular one, is that we are increasing our storage capacity on a certain surface volume, surface area. And the other one is that we are making a fully integrated battery, and that also decreases the amount of full surface occupation. And then, last but not least, is the heat exchangers which we're using. Because one of the key things is that we are going to get heat out of our battery, but because we would like to have heat out of our battery, we need to evaporate water as well. And we're doing this evaporation process at a really low temperature. If we would like to get 60 degrees out of the battery, we are evaporating in the order of 10 to 20 degrees Celsius. Meaning that we have to decouple the process of what is happening in the TCM and what's happening in the component box. And that's what we're doing with help of a heat recovery unit. And the impact of this of the heat exchanger there is really high. Currently we have a performance in the order of 80%, meaning that where we came with an efficiency of 60%. So we improve from a heat recovery efficiency with almost 20%, and that directly impacts the size of your battery. So having a better heat recovery unit will increase the performance and decrease the volume occupation of your battery. And that's one of the major achievements which we did within HEAT-INSYDE. And with that, I would like to finish. And what you see here is the transition to Bart, his work. Thank you.
Thank you, Pim and Henk. I have to say that I know the story for more than 3 years now, but it's still very cool to see where we started and where we are now. And as Pim mentioned, this is a perfect transition towards Bart. So Bart is involved in several technology, and is going to give you a hint about how all these technologies are integrated.
Thank you very much. And because everybody's so fast, I have more time or not? So what I would like to talk about is how we are going to integrate the heat battery into a house. We have 4 different demonstration sites. With the help of our partners, we are going to demonstrate in 3 climate zones. And what I would like to talk to you about is why do we need the battery for heating a house and cooling a house? How can a thermal battery help, and what do we expect of the demonstrations we are going to do in Poland, France, and in Eindhoven? And what's important is also to see what are the different options to implement such a battery in a house. Well, if you look at the current house, houses, then we know that 60% or even more of the energy demand is not for electricity, but for heating and cooling. And what we also see is that the roofs are going to be continuously expand the amount of PV we put on the roof, and it's almost completely full with solar PV. And if we want to renovate houses, then we see also that nowadays we have a problem with the grid connections. So many of the social housing corporations have to ask for enlargement of the grid connection if you move away from gas. And they're simply not easily to enlarge. And waiting times can go up to several years. So what we need to do is find solutions where we do not have to enhance this grid connections. So what we are going to do is actually demonstrate how this heat battery will work in these demonstration sites. With the help of our partners in France, it's CCA and Ventilair-Sec. In Poland, it's Prefasada who helps us. And then in Eindhoven, with the help of Trudeau, we have found one of the houses where we are actually going to install the heat battery in a shed. I will explain later why we do that in a shed. And also we are going to install with a house owner here in Eindhoven, with the help of the municipality of Eindhoven. We found one tenant where we are going to install the heat battery in their house, having a low temperature heating network connection to that house. Each demo site will have a heat pump and the heat battery. And in principle, if you are installing a heat pump, there are 4 typical sources which you can use as a source for this heat pump. First of all, you can use a ground loop as a source, but also air. Of course, one option is also to use sun, regularly known for PVT, so where you have PV panels on the roof with the thermal connections on the back. But we also have a new option, which I will show you. And you can also connect to a low temperature network. Actually, 3 out of these 4 we are going to test in this demonstration site. So I made a short summary. In the Netherlands, here in Eindhoven, we will connect to a low temperature grid. The house of Trudeau will be connected to solar panels where we harvest energy from sun and air. In Gdynia, Poland, we will connect it to a heat pump connected with an air unit outside. And in Cadenet, France, we also connect the system to an air source. So if we are going to use this to install this in a house, then we know that a lot of houses here in Eindhoven, row dwellings, do not have that much space. And if we are going to install a heat battery and a heat pump and buffer vessels, then the already small living space is getting smaller. And that's what we don't want. That's what we don't want for the tenants. The second thing is that we have to move into the house of the tenant and make space and clear up room to actually install this system. So that's why we said, why not go to another solution which was developed in a recent EU project and was demonstrated also in Eindhoven here. We installed a smart heat shed in a house of Trudeau. And the advantage of such a heat shed is that we can actually place it over the house in the garden, connect it to the house, and you have a completely gas-free heating solution. What also is the advantage with this system is that you can prefabricate everything. Still, you need a source. So what we did in the European project is developed several heat harvesting thermal panels, which you can connect to the heat pump as a source. And I just want to jump into that a bit further before we go back to the installation of the heat battery in this shed, which we will go to visit later.
We have developed a novel full renovation concept that harvests thermal and electrical energy from the full building facade, from roofs as well as windows.
60% of the energy demand of a house is needed for heating and cooling. So to harvest that energy, we need more surface area of the facade to harvest that energy. An energy positive building is a building which harvests more energy than it uses.
We use the invisible part of the light we have from the sun. And because of that, we can use all kinds of colors, not only the black, which we are used with the PV panels, but also green or red or blue or gray.
I'm a tenant from Social Housing Corporation Trudeau, and I'm happy as my house is energy positive, free from gas, with a net zero energy bill, and who doesn't want that?
We not only made this facade, we made several facades. It's on the north and on the south. But what made it special is that we also made a little shed with it, and it's only the shed who produces the energy.
We want to implement these kind of technologies more or less for every house all over Europe.
The Envision project has created energy-positive buildings, and with that we can fulfill the 2030 energy ambition of the EU and reduce the greenhouse gas emissions.
We were one of the finalists in the last week's European Sustainable Energy Week, and I'm quite sure that we should also submit our project of HEAT-INSYDE to this for next year or the years after. So the panels which we harvest are based on the fact that we as a human are not seeing all the light. Actually, only 45% of the sun is actually what we see. Also, the near-infrared or UV light can be used to harvest energy. What we did is develop coating solutions which harvest this invisible part of the solar spectrum, which, if you harvest that, could mean 45% solar absorption. In fact, we managed to get 40% solar absorption with white as a source. So these panels actually work as a source for the heat pump and then drive the tap water production and heating. What you just saw was a demonstration site. We did 3 houses in Helmond of Compaan, Social Housing Corporation Compaan in Helmond, and 3 here in Eindhoven from Trudeau. This is actually the shed, and this is actually the shed so as we want to install them now with a heat battery into the houses, into our one house of Trudeau. So this is actually version 2 of the heat shed, and produced now by Emergo, a partner of the Envision project. So we will see this, and these panels which you're actually looking at are the source for the heat pump and is then connected to the heat battery. Now the question is, what is this heat battery doing? So this is a standard heat pump system you could have in your house, where you have a source connect to the heat pump and heats up your tap water vessel or your CV vessel. Now, the difficult thing for a heat pump to do is make tap water, because you have relatively high temperatures, minimum 75 degrees, and once a week also higher temperatures because of Legionella disease. We want to heat up the buffer vessels temporarily, so you need to make hot water of at least 65 degrees now and then. That means that for the heat pump this is very inefficient to do, and with a very low COP. So what we are going to do is charge the heat battery during a day where we have a lot of sun and we cannot put it back on the grid later on. We can use it to charge the heat battery, so the salt will be dehydrated. At the same time, when we dehydrate the heat battery, will also charge the tap water buffer. So we use electricity to charge the battery and also create the tap water. Especially if the electricity prices become negative, which happens regularly throughout this summer, this is a good way of doing it. In the future, it might also be possible in the development of the battery also to use a heat pump to charge the battery. And what we are going to do in times where we actually need then the energy, and try to go to the next slide, is do the opposite. Use the heat battery to create this tap water. And now you see, and maybe the numbers are quite small on the screen, but the bottom tap water vessel of the top tap water vessel is about to 70 degrees, whereas the CV heating vessel is about 45 degrees. So with the heat battery, we are going to create this tap water vessel so that the heat pump can produce at a very high COP the thermal energy for the heating buffer vessel. So what is then the expected end results we will achieve? We already know that if we compare the heat harvesting panels to a regular air heat pump system, that we have a less reduced electricity demand of 30%. That's one. The heat battery will use the excess of heat in moments where the prices become negative to supply energy to the heat battery and charge the battery. And we expect that the COP of tap water production will improve from 2.5 to 6 or even more. And if there's a cold week, we can use the heat battery to discharge several days in these cold periods to create tap water. And this will help reducing the grid loads in these very cold periods, and also increase the amount of self-consumption, so the amount of energy you produce yourself, you are actually going to use yourself. Of course, this battery can also be used to create not only tap water, but also the water for space heating. And that's also what in one of the demo sites will happen. Okay, that was my explanation of how the heat battery helps in the energy system to create tap water with reduced energy. And I also would like to thank Van der Hof installers for helping us with installing the heat battery. And I think it's very nice to visit it later on. Thank you, Mark.
We are ready to welcome our next speaker, but he's going to talk about this storage for balancing energy supply and demand. Marc, stage is yours.
Francesco, thanks a lot for the organization. Olaf, Francesco, thanks a lot for the invitation. I welcome all of you to my presentation, and I have a couple of comments regarding the title. It is simply obvious to all of us that this could be the same village in Germany. It is not, obviously, but I think you all know that there are two different seasons. One is called summer. There is abundance of energy, so we all can celebrate energy parties there. Efficiency is not at all relevant. This is what nature tells us. On the right side, you see same village, basically no irradiation, no energy available with PV or any thermal collectors. If you have a look at the chimneys, there is also no wind, almost no wind available. If you have a look at the roof, there is snow and it feels like cold, so there's a huge demand on thermal energy. So in terms of energy efficiency, I think it's clear that we have to be extremely efficient, because the only source of energy at this, we call it winter time, is formally stored energy resources. I think it's clear. What does this mean for a thermal energy store? I mean, you know, we have a thermal equilibrium. So everything which is hotter than the ambient tends to ambient temperature, right? And so since the duration of the storage from summer to winter is extremely long, we need other solutions than sensible storages. And one is shown here on this video. Everything is at room temperature in the laboratory now, roughly 20 degrees Celsius. And when my colleague is actually opening the valve, in principle, what is happening? What is happening here is that on the left side, there's an exothermal reaction going on, right? The colors tend to red, which is actually showing that the temperature increases, whereas on the right, the endothermal reaction goes on, colors tend to the blue, okay? The interesting thing is here that we do not store thermal energy, we store a chemical potential. I come to this point later on. We have been discussing in one of our meetings in the HEAT-INSYDE project what type of energy we should use. Should it be thermal energy storage for charging or electric energy for charging? Now, this is a diagram which is, again, obvious. It's basically nothing else than a diagram of the two pictures before. In grayish part, you see the demand of energy, and in the yellow part, you see the availability of solar irradiation. It's clear. So we can have thermal collectors with a high efficiency in order to generate thermal energy, put it into our storage, and release it on demand. This changes a bit if we go to an electricity. This is now data, German grid, last year, 2021, all over Germany, and you see that the yellow part is somehow comparable. It is lower, of course, this could be due to efficiencies, but in principle it's comparable. But the main thing which changes is that we can easily transport electricity from our neighbors to our building, or even from the next village to our village, or even further. This is a fundamental difference to thermal energy, and this is why we could include also wind energy here in blue. And you see that they are a bit complementary, I would say. You compare it, at least for the data 2021 in Germany, you see that the heat demand is somehow comparable to the availability of wind electricity. Okay? What changes now is that we do not only talk about one cycle a year, charging in summer and discharging in winter. We can say, okay, we talk about having a bankable energy storage for the peaks or the low parts of the electricity production. This is now weeks or probably months. Of course, they are hardly predictable, so the storage has to be bankable. What does this mean for our thermochemical system? Now, there's a bit more technical details, equilibrium diagrams, here, Van 't Hoff plots. You see on the left an orange line, which is a low temperature charging, thermal charging. In the upper part, we add thermal energy, we release a gas, we have heard this just before the coffee break, and the blue part is actually that we either release it to the ambient or we condense it in a closed system against ambient temperature. The lower part is now the discharging. This is something we have to do in winter. You see, temperatures are lower, pressure is lower, so we need to evaporate water there in order to generate thermal energy again on the left. This is how the video actually looks. If it's working, you see on the left, it's red, on the right, it's blue. Now, if we talk about electric charging, we can change it. We can say, okay, yes, we go to higher temperatures, because electricity we can easily transform in high temperature thermal energy. Now the red one is there. It's charging again at higher temperatures now, releasing our gas, condensing it. At the blue line, everything is identical, except there is a second arrow is missing. And why is that? If you now compare the enthalpies, they are given numbers above the diagrams. You see that on the left side, the operation is rather a heat pump. We absorb thermal energy at low temperatures, 40 kilojoule per mole, use our chemical potential, and generate 60 kilojoule per mole at a temperature which is technically interesting for us. On the right side, you see the difference between these two enthalpies is again 60 kilojoules. So we can say the left side is a heat pump with a storage option. The right side is only a thermal energy store. We just add our two reactants. So this is something you can find on YouTube. Yeah, we have a solid, we simply add liquid water there, and the temperature on the right bottom, it's increasing. It's still slowly increasing. It reaches something like 100 degrees Celsius, and then you see water vapor condensing on the cold glass. And if this happens, water vapor is available and the temperature accelerates, and the final energy or the final temperature in this very sophisticated setup is something like 210 degrees Celsius. What is this type of material? It's so-called quicklime, and we use it at DLR in order to investigate whether we can use it for long-term energy storage. The reason is probably obvious. It's a natural material. It's almost abundantly available. In red, you see karst regions on Earth. So basically all over the world, we could get the material from nature. And on the bottom, you see that if we treat it carefully, we can also dispose it to nature. This is actually where people try to adjust the pH value. We have the chemical reaction with water. This is also nice. There is no chemical degradation there. It's also nice, of course, and we already produce it industrial scale, so we have it in megaton already available. So what is the issue? What is the problem actually with this approach? I do not want to focus on the chemical reaction here, but it's clear that if we have the calcium hydroxide, we cannot squeeze out liquid water out of it, right? We have to add reaction enthalpy, and what we release is water vapor, okay? What you saw on the video is adding liquid water. So in principle, very generic, we are already missing 40% of energy. And the second thing is that it's a high temperature thermochemical reaction. You see the equilibrium is around 500 degrees Celsius. So we need to heat up everything up to 500 degrees Celsius in order to drive the chemical reaction. So we shift our problem, let's say, from availability of water vapor in winter to kind of process integration or system integration, what to do with this thermal energy. So what about the energy balance? Think of using electricity. We have two arrows here. The red one is the sensible heating of our solid. The green one is the supply of our reaction enthalpy, the thing actually that we want to store, right? And this dissociates the compound, so we have two arrows again, the green one and the blue one. The blue one is the water, and the grayish one is the solid. Both contain non-storable or hardly storable energies, thermal energies in the form of sensible and latent heat condensation of water vapor. And the rest is actually what we wanted to have, is our chemical potential, the solid you saw in the video. So if we neglect any energy efficiencies and any technical system, we can simply state that roughly 40% of the electricity we spend in order to charge our system is still available as chemical potential, the video, adding water, right? The rest, 60%, is kind of a thermal energy we should use for daily consumption. And now, let me remind you on this picture at bottom right, this changes. If we talk about electric charging, this means also that we can charge in October and in December and in March with electricity. And there is, of course, thermal energy demand there. This is clear. And so we can think of an integration of these unstorable or hard to store parts of this chemical reaction. So what is our current work at DLR? This is a left picture is actually our setup in Cologne. We develop a system in the middle. You see this white part. This is the reactor, which can be charged and discharged or used for charging and discharging. And on the left and on the right, you see some containers. I cannot show it to you, but you can see them. One is for the calcium hydroxide. Then we transport it into the reactor. We have the chemical reaction there, transport it out, kind of a pellet-based heating system. So you produce your own pellets. That's the only difference. What is inside of this reactor is a mechanically mixed or mechanically induced fluidized bed. You see it on the right picture. There's kind of a tool which is rotating in order to avoid agglomerations and tries to increase the power density of this type of reactor. There is further reading possibilities if you want. My colleague Matthias Schmidt published a paper on it. No experimental results, just the concept is there. We did not publish the experimental results so far. And in terms of integration, we are part of a largest called collaborative research project in Germany, DFG, probably you know that. They are funding universities, fundamental research there, and this large project at the University of Stuttgart built that high-rise building, small high-rise building you see on the picture. This is there now since 1 year, and the idea is that people can test different technologies there and see how they actually behave outside of the laboratory. For us, the most important partner, I mentioned it before, is a partner who knows all or a lot about control technology and control strategies, because we have to understand when do we need thermal energy and when is electric energy available in order to operate our system in such a way that it can be all over the year decent or reach a decent efficiency. Just an outlook. We have the system running now since half a year. We try to build it a bit smaller, put it into a container, and mid of next year, hopefully, we transport the container to this high-rise building and test it there, not to heat up the whole high-rise, this is clear, but hopefully to heat up one floor. And with that outlook, I would like to thank all of you for your attention. Again, thank the consortium that they have me as external, but still it feels like an internal partner of this impressive work here. And of course, my colleague that actually do the job. Thanks a lot.
Thanks a lot, Marc. Nice, very nice presentation, interesting. And now we are, with our last presenter before the panel session, we are abandoning the science and we go more in detail into the policy regulator point of view. Welcome, Nic.
Thank you. Prepared some notes here. Afternoon, everyone. It's good to be here. First event after the pandemic, and it's good to be in person rather than always working through Zooms and Teams calls. But anyway, let's go through the presentation. So I work for TMEIC. TMEIC is Toshiba Mitsubishi Electric Industrial Corporation. And don't worry, I'm not here to do a sales pitch. I'm not trying to sell you anything today. As Francesco said, I'm gonna look at the UK case of the energy storage in the UK. I'm a member of the External Advisory Board, and it's an interesting one because I was involved personally with a startup looking at energy storage for about 10 years. But let's go through the presentation. We all know what happened, what's been happening in Ukraine for the last few months. That has had an impact on gas prices, and obviously that has had an impact on electricity prices because they are inevitably linked, the two together. I'm not going to go into the debate regarding whether pay as bid or pay as clear is the right pricing mechanism. That will take too long, and I think we will need an entirely new session. I'm happy to talk about these later on after the event, perhaps in front of a cold drink. But in my line of business, I work in energy storage in the UK, and I'm going to give you a quick presentation, a few slides more than anything else. Don't want to spend too much time on it regarding the energy storage market in the UK. So I don't know if it's visible, probably a bit too small, some of them, but National Grid has been working on some services for the grid. Some of them through long-term projects with long-term contracts. Others, they've developed some other services which translate into revenues for energy storage projects. One of them is dynamic containment, which was launched at the end of last year. The other two, dynamic regulations and dynamic moderation. And the last two were launched in I think it was June this year, so in 2022. But what they did, so these three services are procured through daily auctions, and that means they're in line with Article 6.9 of the Clean Energy Package, and that sends a clear signal to the energy storage market, and that's what investors need. Olaf mentioned earlier there is a technology, but we need to bring it to market. The market needs to be created, and National Grid in the UK is doing a fantastic job. I don't work for National Grid, but I do believe they're doing a fantastic job in bringing out new services, which send a clear signal to the investors. And it would be great to see other energy system operators around Europe to do the same job. I know some of them are trialing some of these services, but it would be good to see them doing more at a faster rate, especially in the current political developments. Evidence of the market signal in the UK comes from the number of projects that were submitted for planning application. This slide or this graph comes from the Energy Storage News website with data from the Solar Media. Solar Media is a company that gathers data from local authorities. And in 2021 alone, there were almost 12 gigawatts of storage projects submitted in the UK. Most of them, if not all of them, is lithium-ion batteries, because there is a demand for that. There are applications, there are revenues, and therefore the market followed by submitting application, and also in preparation for the other two services that National Grid was working on. But going back going back to the impact that the current political development is having on energy storage, at least in the UK, that the high gas prices, the high electricity prices, and the high volatility in the energy market, well, what that is doing is giving is increasing the market potential or the revenues for energy storage projects. And I've been given special permission to use this slide from IHS Markit, is from a report they've recently released in September. You can see the green bars on the left-hand side there. That was their view, their forecast for the energy storage deployment in the UK. That was in February, before the conflict started. High energy prices, high volatility, meant that the energy storage market, there was more interest in the energy storage market because there were higher revenues. They revised their forecast, and as you can see there, in 2023 they expect almost 2 gigawatts, so more than doubled the expected deployment rate for the next few years until 2030. So that is the market signal. I think to paraphrase a movie that I watched a while ago, so you build it and they will come. If governments and that is my personal opinion, if governments and energy system operators, they bring out new services, whether it is flexibility in or dynamic pricing for electricity, domestic electricity, perhaps technologies like the one we are working on, or the guys here are working on, that can be something that can be utilized, not necessarily for families to make money, but to save in this current climate. One last thing, obviously higher revenues is great if costs remain the same, but that obviously is not always the case. And a slide I've taken from the International Monetary Fund, the materials to sustain the deployment of not just energy storage, but also renewable energy sources. There is scarcity in some of these materials. Scarcity means higher costs, higher prices. And obviously the fact that some of these materials are in the hands of just a few countries doesn't help either. So the impact that the current political development has had on the UK market, in the energy storage market, has been positive because there were higher revenues, but also costs are going up. Main thing is to create the market and let the technology slowly come forward. Thank you.
Now for me is the most important part of the workshop, because we're really hope that we're going to have a lot of questions for you. So I'm going to invite all our 6 speakers to sit on the high chairs there.
René van der Linden. What do you need to increase the development so you have a market-ready product? I saw net in the picture that 2023 we need the product already.
So your question is how we could speed up the development towards a first product.
Yes.
I think speeding up is 2 main components. Let me start by the most simple one from my perspective. That's the technology. And the main challenge, if you talk about the technology, is to make the step from what we're doing now to a real mature first product. And in doing so, what is really very key is that we need interaction with the end user. Because finally the client is determining the success of the product. And for that reason we have the first 3 pilots implemented now that will run in the upcoming, let's say, 1.5 years. So from that perspective you simply cannot speed up. So the shortest period of time is to start about thinking of making a final product after this first validation phase. And then secondly, it's not only about the product, of course, it's also about marketing the product and bringing it towards a real full-speed application. And that means that that we have to find, because in this project we already introduced a vehicle to commercialize the technology, and that's Cellcius. But Cellcius cannot do that alone, because scaling up, speeding up means that you have to find partnerships for large-scale production, large-scale rollout, large-scale distribution. So actually I think it has two phases. The first phase is bringing the technology to real maturity, so translating it into a real product, and secondly has to do with the market development and scaling up. And to be very honest, I think that we started the first steps towards what we are right now some 12 years ago, which is basically, if you think about it, is a very, very fast development of this innovation, this potential innovation. But I think that at least we will need 3 years from now on to bring it to the step that first commercial rollout will take place. And in order to do so, also because this technology has many, many different opportunities for application, meaning a wide range of use cases. There's also a wide range of potential business cases. That also a more profound understanding of what's the, let's say, the winning business case is also something that needs to be speed up in the upcoming years.
Thank you.
Thank you. Yes, we have a question in the back, Emily. Thank you.
It all went a little fast for me, but my question is, why must solar power be integrated in this system? Is that because the output is not enough for heating a house? I guess I missed this explanation.
You're meaning the solar power to charge the battery, is that right? Or what?
No. I just saw that it obviously is necessary to integrate a solar power system in the HEAT-INSYDE system.
Yeah, so the battery on its own has to be charged and discharged. So the charging we are doing with help of any energy which is left over in the house. So thermal energy from your solar panels, electrical energy from your PV panels, or grid electricity can be used as well. So we need that to charge our battery over the year.
I see. So if you can't place solar system on your roof, then you can't use this system, obviously.
The principle you can still use. Of course, it's preferred to have a location on your house or in a surrounding where you have your own renewable energy source. But what is possible as well is taking it from the grid. Technically, that's not an issue at all. Taking the electricity from the grid to charge your battery, that's an option. Economically, at this moment, within the Netherlands, that's not the preferred option because you have this solderingsregels. But yeah, it is technically not an issue to take the electricity from the grid from a windmill or any other source.
Okay, thank you.
And I think that a follow-up for this can be, so now heat pumps are also getting a lot of attention from the media. Does the battery always require a heat pump to operate? So as a follow-up for this question, and how does it change the performance of the heat pump when there is the heat battery?
Yeah, so currently we cannot charge battery with a heat pump. That's one of the things which we're doing right now. We're trying to develop to decrease the charging temperature of the battery. At this moment, we are on the order of 70 till 80 degrees as charging temperature. Within one of the research projects we're doing right now, we are trying to decrease it till 45 degrees. If you look at the performance of a current heat pump, it's performing quite well. At the moment you have high outside temperatures or low temperatures which you would like to have in your house. But especially for tap water, for domestic hot water, or when it's really cold outside, the heat pump, the performance is going down. And that's why at that moment the heat battery in combination with the heat pump is really good, because the heat pump is in their sweet spot and we are in our sweet spot. So the combination of both is quite good, is really interesting technically wise. And to avoid the heat pump, at this moment, especially for the heat battery, that will be non-desired. Of course, when you have sufficient solar collectors on your roof, or also in the winter, an option to have a low temperature system available. So for example, in one of the demo houses in Eindhoven, we are connecting it to Strijp R. They have a low temperature heating network, and these kind of locations, it might be an option in future to get rid of the heat pump. But currently, when you don't have such a source, it will be an issue.
Can I ask a question to Pim? Or a suggestion to Pim? But there could also be another option if you're not charging the salt on the location itself. What about if I just order new recharged salt so that I get new boxes in? Is that an option? And what would that mean for a person?
Yeah, definitely, that's an option. So bringing a charged battery in your home, or just only the active material. So swap the material which you have, like a cartridge. That's definitely an option. Of course, you have a little bit more transport, but in the end, you don't need the hustle of having a charging station in your home. Only a discharging station. So definitely an option.
Thank you, Pim. Yes, we have 2 questions.
Good afternoon. My name is Jos Blom from Coal Industries. The HEAT-INSYDE is working now for One House Solutions. What about more bigger sized solutions if you combine heat storage for a couple of houses or a group of houses? Any developments or ideas on that development?
That's a very good question. I'll only give one example, because there are many examples to give, basically, which is not directly related to HEAT-INSYDE, but it's related to what Cellcius is going to do. The key thing of the heat battery solution that we have is that you can store energy without any loss. As long as it's stored, it's without any loss. That also means that you can transport heat without any loss from A to B. And that's a very interesting business case if you compare that to the existing solutions. Basically, the existing solution is a district heating grid where you're using pipes to bring heat from A to B, and where the distance of transporting heat is very, very limited. So without going into the details, yes, indeed, we are now looking to a very attractive business case where we are going to use or fully exploit the unique selling point of lossless transport of heat from A to B as a kind of alternative or extension to the present district heating grids, which still are a cornerstone in the national and European policy.
I'm not looking for a competitor of heat networks, but I worked with heat networks many times in my former employee, and they decided that the best solution for a local heat network is a group of houses or an apartment complex. So it's in between heat networks and one house solution. I think the heat battery will be fit in quite well over there.
Yes, I fully agree. And the main advantage is that because of the modular design that we have chosen in HEAT-INSYDE, you can easily scale it up or scale it down. And that's one of the key things, yes.
Thank you. I think there was another question here. Thank you.
Hello, I'm Frank Fransen, and I understood that your apparatus does 2 things. It stores heat and it produces heat. And now when houses are very good isolated, you have only in the winter a very short time where you need heat, and that's exactly the time that you cannot produce heat. So I think you should split the apparatus into two separated, one that produces heat and the other that stores heat. But now I get an apparatus in my house that will store heat at the time I don't need it, and when I need it, it doesn't produce heat. Did I understand it correctly, or?
I'm trying to answer this correctly.
You understand what my problem?
Yeah, partially. So, I think so. I'm trying to tell it in my own words, and please correct me if I'm wrong. So, if I understand you correctly, you're saying, okay, we are storing the heat, especially in the summer period. We can store the heat.
But then I don't need it.
But you don't need it, true. And in the winter, you cannot store anything anymore because there's no leftover energy anymore, but you are discharging it. So you are looking more for a seasonal storage application, in fact. As storing it really during the summer and discharging it during the winter.
Yeah, but when you have a very good isolated house, the period you need to heat your house is very small.
That's right.
And it becomes more and more houses are becoming isolated very well. So I don't think I will need this device.
I think that you're fully right. If you have a very well insulated house in wintertime, you hardly have any needs for additional heat.
Yeah.
Yes, but there is another thing, and that's the one thing that I've been putting forward, is that you can also use the same device for cooling. And if you have a very well insulated house, then the problem is shifting from heating to cooling. One of the key problems that Finnish houses are facing, for example, is not related to heating, but to cooling. So my answer to you is yes, in wintertime you will hardly use any storage device. But in summertime, if you have a very well insulated house, you will definitely need a cooling device.
Well, I have a very good isolated house, and I just opened the windows and the door. I came to the summer perfectly.
Yeah.
We have over question. Yeah, sure.
I was impressed by the opportunities with quicklime. I think the high temperature release could be used. Now we're talking about heating houses and apartments, but for industrial heat, there's no solution yet, and everybody wants to burn hydrogen. That seems as a bad idea. So probably in summertime you can charge that quicklime and use that heat in the wintertime for the high temperature industry.
Yes, it's a good point, very good point. Of course, the medium temperature, let's say for steam production in industrial processes, is of course challenging, even more challenging the last month. It's clear, but I would say, I work in a department where we work on different type of thermal energy storage technologies. And I think at the moment, other physical storage technologies that actually cover 2, 3, 4 days of storage capacity are, in terms of industrial processes, more interesting than the seasonal or the long-term storage, right? Because this is, it's not an emotional thing, it's a purely economical thing there, right? What is the best in terms of economics solution? But what I would like to add here is that playing with the temperatures allows you to integrate unused industrial, we call it waste heat, right? So you can take it up and then pump it to a higher temperature level, and this on a continuously driven basis, right? Kind of a high temperature heat pump, but chemically driven. This is a topic we address, of course.
And what temperature jump you can make with this quicklime?
Yes, temperature jump is based on the pressure difference between the condensation and let's say we have 100 degrees Celsius waste heat to drive, and you can condense against, let's say, 45 degrees Celsius ambient. Then you have something like 70 Kelvin of temperature jump. But this happens at 450 degrees Celsius. So changing the reaction system to a system which operates at 200 or 150 or 100 degrees Celsius is of course possible, but was not a topic of today, but this is some we can discuss probably afterwards.
But then you're a competitor of acoustic heat pumps.
Of course, yes, for instance, yes.
Thank you. We have a question here.
Thank you. Arno Vlooswijk, infrared photographer, World of Warmth. Fascinating technology. A question about would it be possible to make an indoor version? If a bat is hibernating in a cave, it warms up from 4 degrees to 70 to 37 degrees without solar energy, without environmental warmth, by brown fat. It's fat stored inside its back. You have hand warmers, so you have small salt with the iron disc. You can create salt warmth. Is there a version of this concept by salt which could be placed inside this room, like an indoor version, closer to the people, because you don't want to heat houses, but you want to create comfort for the people inside houses. So more indoor, like a couch or a table or a small wall, with the same basic blocks.
I have a microphone here.
It's a biology question.
It's definitely a good suggestion. At this moment, with the technology which we have, we don't have it like that. We're not developing right now or in that way, but we will definitely put it on the list. But maybe one of the others already had it in mind, but no, we didn't. But I think it's a good suggestion. But at this moment, we're not developing it like that.
Okay, thank you.
I do have a question for Henk, our material guy. How about the sustainability and safety? Because people are going to put these in their houses.
Okay, that's of course, and I think the point was a bit also touched by Nic in his presentation. So whatever we're going to do with renewable resources, and even for storage material, you have to think about recyclability. That's one thing we took into account already from the start on. So in selecting the material, and the material was selected in the predecessor of this project, we have assessed based on several aspects, the technical aspects, but also on things like costs and, let's say, hazardous impact. And we now use potassium carbonate. Together with Kaldik and Evonik, we came to this product. And to give you an indication, that's at the moment used in the food industry, it's used in fertilizer industry. It's fully recyclable, the material we have now. And I can state that really quite directly. And the other thing to keep in mind, and maybe that's, I think, a nice side product of this, in the production of potassium carbonate, you capture basically CO2. So, as the word says, carbonate is basically consisting of partly of formerly CO2 from the environment. Gives you a bit of a flavor of how we came to this particular salt, because it's a salt.
Thank you, Henk. Yes.
Good afternoon. My name is Olaf Adan, and I have the following question. Let's say you have an ordinary house which has a capacity usual of traditional 2,000 cubic meters of gas through the year. How much units do you need to get through a whole year for your capacity?
If we're talking about units, we showed you now a 200 megajoule unit. You're talking about 2,000, so in the order of 20 square meter of active material. That's a little bit the order where you're talking about. And that's also the reason that we as HEAT-INSYDE have the impression that only seasonal storage will be not that realistic on short term.
Okay, so you can't storage for a whole year of energy. That's not
It is possible, and of course I would like to sell it. I think the guys from Galdic really likes to sell this amount of salt, but no, we think it's economically not favorable at this moment.
And you are saying 2,000 square meters for, but
no, sorry, 20 cubic meter of
20
active
cubic
material,
meter, okay.
of active material.
And how much of these units are that?
So currently we have 300 liter of active, 0.3 liter of active material in it. But what I said, it is quite modular, so we can have a little bit different component box, but add then the 20 cubic meter of active material next to it. So it's not that you really have to buy, let's do the calculation, but 60 of these kind of batteries. You need the active material, and you need a few heat exchangers with that. Okay, this is really downgrading the component box, but yes, something like that.
Okay, thank you.
I think we also have a question. Yeah, here first, and then we're coming back to you. Here in the second line, Emily. Thank you.
Thank you. For the salt material, the cycles that you can make, are they limited, or can you make other cycles all the time, and don't you have to replace the material?
The material, let's say on the tablet level, we can cycle for approximately 200 times. Don't have then chemical degradation, but basically then you get mechanical integrity problems. And then you have to come up with, let's say, a new shaped particle. So basically what you can do is reshape the particle again and then use it again.
Yeah, we first in the last row, sorry.
One more question. Shouldn't we be afraid that this equipment is too complex for the average house owner? I mean, you have to watch it all the time, I think.
I think there is a great question. I think that Bart already has the microphone in his hand.
I want to give it to my neighbor, no. I'll try to answer. I think that if you make such a system like the battery now, we are going to fully automate the battery. There's a lot of control in it. It works together also with the heat pump, and that automatically will signal us if there's something not going right. And with the shed especially, we devised a back door for the installer, so that in the corridor behind your house, where you normally go with the bikes to your back garden, you can access the installation room. So actually in one of the houses here in Eindhoven with Trudeau, we have this shed installed, and actually we got an error because there was a tiny leak, and then the installer was notified, and before the tenant knew that there was something wrong, we already fixed the problem. So I think that all the systems we are getting in your house today have some kind of connection to the grid, not only to monitor the grid, but also send signals if something is going wrong. So I think that there's no reason for a worry there, because we can fully solve that issue.
And this is going to be the case as well for the final product?
That's a good question, but then I move the microphone to Pim.
Yeah. So I think there's a difference between the current product and the final product. So at this moment we're still in the research phase. We're really testing it with limited knowledge. We are really testing it for a long run to see how it functions by the end user. At the moment it works, or we will really commercialize it. The performance will be way more stable, and we have way better knowledge about how it works. I think a heat pump, but also it's also quite complex. And as an end user, you should not touch it. And that's also with the heat battery. At the moment, we will develop it. We will make it in such a way that it is safe, stable, and fully proof. We call it in the lab professor-proof, but that's what we are trying to develop. So it should be really safe, and you as an end user should not be worried about it at all.
Okay, thank you. Thank you. Yeah, we have 1, 2, 3.
Hi, my name is Joep. I have two questions, one really short one, I think. You said the material was fully recyclable. Does that mean that it can be, after it's mechanically degraded, that it can be just pressed into the same grains over and over?
Short answer for the recording, yes.
Yes, okay. Yeah, that was the answer I was looking for. Perfect. Then the other question, I was naively hopeful that this would be the solution for seasonal storage. Unfortunately, it's not, I just heard. But how does the the domestic heat storage business case look like, and what are the costs and what are the profit margins? Like, how does this generally look? Like, what do you expect? I understand it's still a professor proof stage, but
okay. So the first thing is about seasonal storage. My answer to that is really straightforward. From the technical point of view, there is no objection for seasonal storage. None at all. But from the economic point of view, it is. Basically, if you're using, the example was already there, a big amount of salt and use it for seasonal storage, you are only using it once a year. So in our way of thinking, it is, and that accounts for nearly every seasonal storage. There is one escape route, and route that's moving to indeed a very big storage level to serve a lot of end users. Then it might become economically attractive, but in our case it's not, as with other solutions. And with respect to the business case, that's a very complicated question to answer, because it highly depends on the configuration. It highly depends on the number of end users. It highly depends on the volumes that you're using. So I cannot answer that question straightforward, but there are business cases that are very attractive, and there are business cases that are hardly attractive. That's the simple answer.
Thank you. So if I would ask for a quick number, like how much would 1 kilowatt hour of storage cost?
Well, we think that for, once again, that's still because we are in the process of validating the technology. But to give an indication, we think that for a typical household application, so this kind of application, you will have to think about something like 10 euros per megajoule. So can you recalculate that? I have to ask my assistant because...
I think we will calculate after the meeting.
Yeah.
Might be better. Thank you.
Yeah, thanks a lot for the questions. I think we have one question in the back.
My name is Gerrit Brenissen. My question is, do you have any idea when this unit is on the market and you can buy it as a house owner? For instance, for peak shaving during 2 weeks, what would be the price level, the level of investment costs, in the case that it would be manufactured in serial production?
Once again, that's a very good question, but it's still not, I'm still not capable of answering that in terms of exactly what would be the cost. But the first thing is that entering the market is foreseen after 2025. And I cannot be more explicit about that because we're still facing a lot of uncertainties. Secondly, if you just think about the numbers that I've just mentioned as an indication, then a typical system, but it's highly dependent on the configuration and the size, will cost a couple of thousands of euros. And that's the only thing I can say at this moment.
Yeah, that could be 2 or 10. these thousands.
Depending on the size, of course.
But well, when you have the purpose to make a solution for houses, then it would be a must to have a level of investment costs for the house owner. If it would be too high price, then it would never get a place in the market, of course.
I can only say yes. I can only agree with that. But the reason why I'm just not capable of answering your question is that we are still in the process of making a profound market analysis, because this is a typical example of a single kind of application, but you have many more applications also for collective heating. And as far as I can say now is that the business cases for collective heating are much more attractive than for individual heating solutions.
Yeah, that's right. May I put a second question? There's a short one. What would be the lifetime of such a unit?
So if you look at the unit, we have quite a lot of components which are not moving at all. So we have heat exchangers, we have the salt itself, and we have a ventilator. That is simply saying that's what's inside the battery. The fans have, of course, limited lifetime. The rest will sustain for quite a long time. The material we have to swap sometimes at the moment, and it's not stable enough, or at least it's, the pressure drop is getting too high. But we're talking about a system which will stay between the 15 and the 30 years. At this moment, we're developing it for 15 years. And there might be, depending on how often you're running the battery, we have to swap the fans. But that's the only active moving part in the battery. So compared with the heat pump, that's why we say, okay, 15 years, more or less where we are targeting on.
Thank you. I think we have a bit more here in front, a question.
I have a question for Bart. I think in the beginning you mentioned that we have a problem in the Netherlands and probably elsewhere as well, that we have to enlarge the grid connection. But if this heat battery always needs to be in a combination of a heat pump, will we still need to enlarge the energy connection?
Well, I think that the heat battery will help in reducing the load in such a way, and with the COP of a heat pump, that you can run heating of the houses with one single phase. So if you have one phase connection, if you have a row dwelling and you insulate it well, so you insulate the wall, roof, floor, double glass, then you see that the energy demand drops to 3-4 kilowatt peak in the winter, what you would need. If you then have a COP of 3-4, that means 1 kilowatt electrical. Of course, everybody is going to use the grid at the same time, and the grids were designed in, let's say, when the houses were built for, let's say, 1.5 to 2 kilowatts continuously. And by having then the heat battery in, you can kind of use the heat pump way more efficient with a higher COP. And that means that the demand is lower. So even if the whole urban area would then have the same system installed, the heat battery will help in reducing this the electricity demand. Of course, it depends on the local grid and the whole scenario. But there are studies done which show that if all houses in an urban area install a heat pump at the same time, and then it's cold, especially an air heat pump, then the electricity demand will be way too high. But by combining it with a heat battery or even with some solar input, then the levels would drop. Of course, you need to do a calculation together with the grid network provider to see what's the case in a certain urban area. So it's not a general rule, but I think it will work out.
Thanks. Yeah, I definitely think that it's a good solution also for the indexes in our case.
Yeah, and maybe also interesting to add on that, the coldest days we have in the Netherlands, where it's -12 in the night, is because we have a clear sky. So we radiate as the houses radiate to the sky. That's why it gets cold, -12. And if you do an analysis of the last 10 years here in Eindhoven, you will see that during the day in front or after this cold night, there's also a very sunny day. So during the day, we have a lot of sunshine. So you can also balance, let's say, the grid also by using solar input. So we were discussing, let's say, to bridge, let's say the seasons, but we can do a lot also by just using the energy we have available during those periods, which also reduce a lot. So I think the combination is in doing both.
Yeah. And following on this topic, can you give the microphone to Nic?
Yes, of course.
Yes, it's you, Nic. And but following this way of thinking, so if will be less need to, let's say, modernize the infrastructure for the electricity grid, do you expect there will be, since municipality and government are saving money thanks to this new technology, do you expect that they will do something to facilitate the installation and forward to the market of this type of tax?
That's a very good question, and as I said earlier, the grid was built 70, 80, probably 100 years ago. It was built or designed for a centralized type generation with large power plants and all the end users. There was no idea that 100 years later there would be electric vehicles, heat pumps, and solar panels and on every house, and so inevitably grid expansion has to be part of the solution to be able to handle the amount of renewable energy that we're trying to generate. We're only generating with wind probably 50% of the time, if you like, on the offshore and less in the onshore wind farms. Sun PV farms, they generate probably 30-40% of the year at peak level. So you need to generate 3-4 times the amount that you actually need, taking into account also round-trip efficiency and the efficiency of storage and everything else. So I think inevitably grids will need to be expanded. Storage at domestic level will certainly help to reduce that need, but that will be certainly part of the solution.
Thank you, Nic. I think we had just you solved. Yeah, good. I think I was hearing from there was another question. Yeah. Oh, thank you, Eva.
Tino Oostam, what is the max percentage of charge and uncharge of the battery?
At this moment, we can do a fully charging and discharging. So there's no issue like with the battery that you are doing an overcharging or undercharging. Of course, at the moment you have a fully charging or fully discharging. The last few percentage, the power output will lower a bit, but the temperatures are still the same.
Okay, and one more question about that. Do all the cassettes in the battery have the same value, or can you take half out and replace them with full ones?
Yeah, so not all the 10 boxes has to be charged or discharged. So we can do a few already charged. It can also be partially charged or discharged. That's not an issue. So we only have to do good bookkeeping. That's the most important thing.
Thank you. Sure. Here.
How much time does it take to charge one battery, one cassette?
Yeah, one cassette, and that depends, of course, on your power which you can put in. We develop it now between 500 and 4 kilowatts, 500 watt and 4 kilowatts. So at the moment we have an average of 2 kilowatt. We're talking about 2 to 3 hours.
think we have still time for a couple of questions.
I was just wondering, for the far, far future, when we all have this battery in our shed, is there a possibility, or do you foresee a possibility that the battery cells can regenerate themselves when they are degraded? So if I understand, the chips are...
Henry.
Or does that needs to be something in a big plant?
No, at this moment, maybe in far future, but at this moment, that's also the way we are now building it up, is that we can take out the cassette and we can swap it, and we bring the cassette back to the factory. We take out the material, we press new tablets, and we fill it again. So I'm not foreseeing it on short notice that we will do it in-house.
But in the far, far future?
You never know.
Thanks.
Good. I think it was a pretty long discussion, so really enjoyed it, and I really hope that you can also all join us at the e-shed, so you can really look at yourself and keep asking questions there. But before moving, I'd like to swap spots with Olaf for some closing remark for the discussion. You want to come here? Yeah.
Yes. I think this afternoon it was really, really my privilege to introduce the heat battery, the first loss-free heat battery, to a wider audience. And Pim was showing that we started with some pictures, and you have seen that the system was growing and was shrinking even more and growing again. But those are still pictures, so the only thing that is needed to convince you as an audience to see it real life, and that we really did the job. So it's about a development that started some 12 years ago, and we have seen an enormous acceleration in the past 3 years with different prototypes. Prototypes that eventually, and Pim stated that very clearly, need to be professor-proof. But I think that's not the only thing, because it's talking about a lot of technology. And what's even more important, and that's what I was trying to say in my opening statements, is this is not only about technology, this is about bringing technology to real application. And for that, we need interaction with end users or users in different ways, like you. So in order to close this meeting, it's always, it's commonly done to say a few thanks, but I would like to start with thanking the audience, because this interaction is also really helping to speed up our innovation. So thank you very much. And then, of course, I also have to thank the speakers of this afternoon, and particularly those 2 speakers that came from abroad. So thank you again. And my final words is, before inviting you to join us to move to the heat shed, is to thank also Francesco and all the others that supported you in organizing this meeting. So thank you very much.